The peer-to-peer server now broadcasts transactions to individuals on the network in the same way it sends blockchains for synchronization. As we added this transaction synchronization, we updated the format for how messages are sent over sockets on the network. Therefore, we'll need to update the message handler function, which actually runs the relevant code depending on those incoming transactions. The first portion of the message handler function can be left the same in terms of listening for the message event and parsing the message as data. However, we'll need some additional logic now after the data is parsed. Now, rather than immediately calling the replace chain function, we'll run a switch statement based off of the incoming data type. So we'll switch based off of the data.type, and this switch statement allows us to run different cases depending on that different type to execute different code. So for our first case, well, let's handle a message type which matches the message underscore types dot chain message. So if the message contains a type which is message types dot chain, meaning it received one of these socket send chain calls with the type of message types dot chain, well, we'll execute whatever we handle under the case message types dot chain. In this case, we'll carry on with the original behavior and replace a chain with the chain that is included within the data object. So we'll say this.blockchain, go ahead and replace your chain with the incoming data, and this time we'll have to access the chain field since that's what we put it under when we sent a message types chain message. And now we can delete this last line. One thing with switch statement cases is that you need a break statement after each case so that you don't continue with the rest of the switch. Now we can go on to the next case, which is the transaction case. So message types dot transaction. And in this case, we'll want to update or add the incoming transaction to the user's transaction pool. So let's use the transaction pool of this server and call its update or add transaction function. So we'll call this.transaction pool dot update or add transaction. And then what is the transaction we want to add? Well, it's the one that is within the data under the transaction field, since that's how we sent it in the send transaction function. Likewise, we want the break statement so that way it escapes the switch statement. Excellent. Now our peer-to-peer server serves two functions. One, it synchronizes blockchains. And two, it keeps a transaction pool up to date. All right, with this peer-to-peer server update, the last step is to actually use this broadcast transaction function whenever we create transactions with the transact endpoint in our application. So within app/index.js, let's go to the transact endpoint. And then what we want to do is broadcast a transaction we created over here using the peer-to-peer server. So right at the top, the peer-to-peer server variable name is P2P server. So after we create the transaction, let's call P2P server. And then we'll broadcast this new transaction by using the new broadcast transaction function and then passing in the created transaction object as a result of wallet.createTransaction. Excellent. Now the transactions are actually going to broadcast across the network and our message handlers will add them to the transaction pool. Let's test this new functionality out and check that pools are indeed synchronizing across peers when new transactions are submitted. So we're going to do this in the command line. So go ahead and open up a new instance of the command line, and then you want to run the application, so use npm run dev, and then this one will run on the normal localhost port 3001. Now we'll go to another tab and open up a second instance that connects to the first one. So as we create a second instance, well, we have to change the default ports. So for the first port that we're changing the HTTP port, and let's make it 3002 since 3001 is taken. Likewise, we'll change the peer-to-peer port, and this one is 5002 since 5001 is taken by the default. We'll specify one of our peers, and then this one is the WebSocket address of that first instance, which is ws://localhost port 5001. And then finally, we can run the application normally by using npm run dev, and then these change environment variables will be passed to the running application. All right, as we do so, looks like the socket connected and it's running on port 3002. Excellent. So let's experiment with this in Postman. Go ahead and open up the Postman application. First up, hopefully you still have the Transact post endpoint still loaded on your Postman application. If not, not to worry. Make sure you have a post endpoint. It's localhost port 3001/transact. Go to the body section. Make sure you do raw JSON application/JSON. And then the JSON that you're sending needs a recipient key and an amount key with the respective values. All right, let's hit this first endpoint a couple times to send some transactions using the first instance. So we'll click send a couple times, and then the result is a list of transactions, which contains our one transaction object with the multiple outputs to represent how many times we performed the transaction. Great. Now, the more interesting part is what happens if we ask to see the transactions that are within the pool of not just this instance, but the second instance. So we'll make a new get endpoint that hits localhost port 3001/transactions. And then this should return the same result that we saw as a result of the transact endpoint on the first instance. And actually, we're going to hit 3002 since that represents the second instance. All right, as we do so, hitting the transactions endpoint of the second instance indeed returns the transactions that were present from the first one. Great, so it looks like the pools are synchronized. Likewise, if we hit the endpoint of the first one under localhost 3001, well, we get the same result. Excellent. This means that our peer-to-peer server synchronized the pool across the running instances of the application. All right, let's test it out one more time by making a transaction with the second instance's wallet. So back in the post tab, instead of hitting localhost 3001/transact, let's hit localhost 3002/transact. And then if you want, you can also change the recipient address just for some diversity in the way the data looks. All right, let's click send on this. And then this time, as we scroll down in Postman, the overall object should have two transaction objects, and indeed they do. There's a lot of data to see, but this part over here shows that this is the end of the first transaction object, and then this is the start of the second one for the bar address. And now let's hit both of the transaction endpoints on both instances. So first, localhost 3001/transactions. Again, it's a lot of data, but here we see the bar address transaction, and then 3002/transactions just as well. Shows that we have the full data list. Excellent. So with that, we have a list of transactions consisting of more than one element, since we've generated transactions from both wallets. Very cool. This proves that we have a transaction pool that stays up to date as transactions are updated across the network by individual users. Continuing with the project, we'll start to incorporate these transactions within the actual blockchain implementation. The next big step will be to take a group of these transactions in the pool and then use that as a piece of data to store on the blockchain. All right, let's move on.